Does the Earth have a hum, and does it affect us? Lately, I've been coming across posts like these on social media pretty often. Maybe you've seen them too. They're usually accompanied by captions about reconstruction of our reality, jumping the timeline, going into 5D, and so on. They talk about blackouts, whiteouts, energy, spirituality, spatial anomalies. I think it should be obvious to the overwhelming majority of you that all of this is complete nonsense. But there is one catch. If the text in these posts is nonsense, these images are actually real, captured by real scientific instruments, and maybe someone looking at them will think, what is that? Maybe there really is something to it, especially when it is dressed up with a very serious sounding name, Schumann Resonance. Here's an interesting thing I noticed. If you search for the phrase Schumann Resonance on almost any social media platform, most of the results will be nonsense like one I just told you. And yet the phenomenon itself is very real and scientists have been studying it for decades. But in the constant stream of social media content, it's hard to come across any reliable information about it, especially the kind of information that naturally shows up in your algorithm. You can find something sensible only if you directly search for it, and even then you'll have to filter through a lot of nonsense. In general, this is yet another example of how esotericists take some real scientific phenomenon, concept, or simply a scientific term and try to use it to legitimize what they do. They especially love doing this with quantum mechanics, the observer effect, you change reality, and all that stuff. It's a shame they couldn't be bothered to read even a slightly more detailed and reliable source on the subject, because then they would have realized that everything they're saying is nonsense. The story with the Schumann resonance is very similar, but the phenomenon itself is actually very interesting, even without the claims made by esotericists and other alternative thinkers and pseudoscience enjoyers. So today we're going to take a closer look at what the Schumann resonance actually is, what causes it, how it was discovered, whether it exists on other planets, and why scientists study it. Let's try to figure out whether this resonance can actually have any effect on humans. And of course, we'll take a look at some more amusing claims made by those guys. There is no shortage of them. Time speeding up, bracelets that supposedly synchronize you with the pulse of the Earth. And when they make posts with these images, they don't even understand what they're actually looking at in these graphs or spectrograms. Well, no worries. We'll tell them what they're actually showing. I'm Andrei, and this is Cosmos Elementary. Let's start by figuring out what these resonances actually are. Some people call Schumann resonances the hum, pulse, or heartbeat of the Earth. But in reality, the brief definition would sound something like this. The Schumann resonance is the formation of standing electromagnetic waves at extremely low frequencies between Earth's surface and its ionosphere. Somehow that doesn't sound very mystical so far, but now let's take a closer look at the nature of this phenomenon. Let's start with the fact that we are surrounded by electromagnetic radiation everywhere. The type of electromagnetic radiation we encounter most directly is, of course, visible light from the sun and from artificial sources. We're also surrounded by electromagnetic waves with much longer wavelengths. I'm talking about radio waves, of course, and we can't see them with our eyes, but in reality we're literally immersed in them. And these are not only artificial sources like cellular networks, Wi-Fi, TV and radio broadcasts, but also natural sources. First and foremost, of course, our sun is a powerful source of radio emissions. They can also come from objects beyond the solar system, such as other stars, pulsars, extragalactic objects such as quasars and many others. Here on Earth, these include activity in the ionosphere, various forms of atmospheric activity such as lightning, and so on. Let's imagine an isotropic source of radiation. Every individual photon or wave emitted by this source will travel freely through the universe until it encounters something it can interact with. If that happens, the photon can be absorbed, scattered, refracted, or reflected, depending on the properties of the material it interacts with, as well as the wavelength of the photon. We can't see the light from the lamp in a closed room next door. But Wi-Fi radio signals from a modem can easily pass through a wall, and our phones have no trouble picking them up. The second thing we need to remember is that electromagnetic radiation gets weaker with distance. Let's recall the inverse square law, according to which the intensity of radiation is inversely proportional to the square of the distance. Twice as far from the source, the radiation is 4 times weaker. 10 times farther away, it is 100 times weaker, and so on. But the point is not that individual photons become weaker. Rather, the number of photons is finite, and as the rays spread out from an isotropic emitter, fewer photons hit the same area as the distance increases. And sometimes this can be a problem. For example, when we need to send a signal to a specific point, but it's also spreading out in every direction, including all the directions we don't need. I want to send a signal with this lamp over there, but for some reason the light is also going over here and there. There are various ways to counteract the weakening of radiation with distance. The most obvious one is to focus it. In the case of lights, we can produce collimated radiation, as with lasers, where, under ideal conditions, the rays travel parallel to each other instead of spreading out in different directions, allowing the intensity to be maintained over a greater distance. Of course, ideal conditions don't exist, but still. And in certain situations, we can also use waveguides. A similar problem arises not only with electromagnetic waves, but also with sound waves, which also weaken with distance. Imagine you need to call out to a friend who is standing, say, 500 meters or yards away. So you shout to him. When you shout, the sound coming out of your mouth doesn't just travel toward him. It spreads out in all directions. Sound waves propagate from you approximately as a hemisphere, because you're standing on the ground rather than floating in the air. If you were, you'd have a sphere. Of course, it's not perfectly symmetrical in terms of signal intensity, because it also depends on which way your head is turned. But still, when you shout, people can hear you even from behind. Waves carry energy, and if your goal is to simply reach your friend, all the sound traveling in other directions is energy wasted. And the signal once again weakens significantly with distance. But there is a way to fix that. You shouldn't just shout. You should shout into a tube. Maybe you've seen those tubes at playgrounds or in parks that go into the ground and then come back up somewhere farther away. Two people can stand at opposite ends of the tube, with the one putting their ear to it while the other speaks or even whispers. And despite the considerable distance between them, the sound travels perfectly well to the other person. So in this case, the tube literally restricts the spread of the waves in all directions, allowing the sound waves to travel farther with much lower losses. Even with a simple tube like this, if I point it away from the microphone and say, you'll notice the difference in sound, because now the waves from my mouth aren't spreading in all directions, they are going past it. A tube like this is an example of an acoustic waveguide. There are also optical waveguides. For example, most of you are probably familiar with optical fiber, whether in lamps like these or in fiber optic cables. Here too, the light waves are repeatedly reflected off the inner surface of the cable and ultimately reach the receiver instead of spreading uselessly in all directions into the surrounding medium. There are waveguides for other types of radiation as well. Microwave waveguides. You have one of these in your microwave oven at home. There are waveguides for radio waves. The principle here is similar to that of optical fiber, but because radio waves have longer wavelengths, these waveguides are also larger. They can be hollow tubes like this, inside which radio waves propagate with a specific range of frequencies or wavelengths. They come in different shapes, sizes, and designs, and are used in many applications where radio signals need to be transmitted with minimal losses. Waveguides can often perform better than coaxial cables, which may have higher losses. But why did I even go on this tangent? Well, here's why. Yes, we've learned how to create waveguides of different kinds for different purposes. But waveguides can also occur naturally, and the Schumann Resonance occurs in exactly such a natural waveguide, one that is literally created by our entire planet. In the examples of waveguides I've just given, we had some kind of structure that confined the propagation of electromagnetic or acoustic waves at certain frequencies. our planet can do the same thing. Our Earth is made up of multiple layers, and both the planet itself and what lies above its surface, that is, the atmosphere, are made up of different layers. These layers, both beneath our feet and above our heads, differ from one another in their properties. And right now we're particularly interested in 3 layers. First, there is the Earth's surface. Second, there is the upper region of the Earth's atmosphere, specifically the ionosphere. And finally, there is everything in between these 2 layers. The basic idea is that this 3-layer system can act as a waveguide for certain frequencies, specifically radio waves with extremely long wavelengths or extremely low frequencies. For this to work, we need electrically conductive layers on both sides. That's exactly what the Earth's surface and the ionosphere provide. The ionosphere is a region of the upper atmosphere that encompasses parts of the mesosphere and thermosphere. Of course, there is no sharp boundary between them, and the ionosphere itself is divided into 3 regions. The lowest layer, the D layer, begins at an altitude of about 70 kilometers or about 43 miles. E layer at around 100 kilometers or about 62 miles. And the F layer starts even higher at about 150 kilometers or 93 miles, and it extends hundreds of kilometers or miles upward. The defining feature of the ionosphere is the presence of ions, charged particles that are created when ultraviolet and X-ray radiation from the sun interacts with neutral atoms and gas molecules in the upper layers of the atmosphere. As a result of this interaction, electrons are, roughly speaking, knocked off these particles, causing them to become charged particles or ions. The auroras occur in the ionosphere along with the atmosphere's own air glow. In short, it's packed with charged particles, making it an electrically conductive layer as well. So we have these 2 conductive layers with the lower layers of the atmosphere in between, which are much less electrically conductive, and this layer acts as the cavity of the waveguide. So in the end we get something like this, only on a planetary scale. Waveguides don't necessarily have to be straight. Think back to the example of the tubes in the park and the acoustic waveguide. And radio waveguides don't have to be straight either. Here our waveguide is closed, essentially wrapping around the entire planet. This means that radio waves can bounce back and forth between the Earth's surface and the ionosphere many times instead of being absorbed by the ground or escaping into space, effectively circling the Earth. Someone might have a question here. I said we need 2 electrically conductive layers, but in artificial waveguides, the walls are the same on all sides. Here, on one side we have the dense, massive Earth, and on the other, just some gases floating around, albeit charged ones. That's the first thing. Secondly, some of you may have remembered that our atmosphere is largely transparent not only to visible light, but also to radio waves. That's why radio telescopes can work quite effectively from Earth. And that's true, but radio waves is a broad term. In fact, our atmosphere is opaque to most of the electromagnetic spectrum. It doesn't let gamma rays or X-rays through, and it barely lets ultraviolet radiation through. Infrared radiation and microwaves also have a hard time reaching the ground. As you can see clearly in this diagram, there are essentially only 2 windows at the surface: the optical or visible window and the radio window. And we can also see here that radio waves with longer wavelengths don't reach the surface. And it's largely the ionosphere that blocks this kind of radiation. Low-frequency radio waves or radio waves with longer wavelengths coming from some cosmic sources are reflected by the ionosphere and then sent back out into space. The same thing can happen in the opposite direction. In fact, this was even used for communication in the past. In my video about the Haarp project, I talked about how before the advent of communication satellites, there was a problem with transmitting radio signals over long distances on Earth. Thing is that electromagnetic signals travel in straight lines, and under normal conditions, the receiver needs to be within the transmitter's line of sight. But the Earth, how should I put it? It's not flat, so sooner or later, even the tallest radio tower will disappear below the horizon. And transmitting a signal directly between 2 points on Earth, separated by thousands of kilometers or miles, is no longer possible because of Earth's curvature. And this is where engineers and scientists came up with the over-horizon radar systems. They make use of the ionosphere's ability to reflect radio waves at certain frequencies or wavelengths, allowing signals to be transmitted over thousands of kilometers by bouncing them off the ionosphere and beyond the horizon. I even personally know some amateur radio operators who have bounced signals off the ionosphere themselves and received them back. So we've now described the environment in which the Schumann resonance occurs. And now for the main question, what exactly is the resonance? Oscillating systems can have a natural frequency or resonant frequency. It's a frequency at which the system responds to an external force or oscillation with the maximum increase in the amplitude of its oscillations. For example, you can stretch a spring, pluck it like a string, and it will oscillate for a while. That's our oscillating system. Now, if we attach a mechanism to the spring that keeps shaking it continuously, the spring will, well, keep shaking. But if the mechanism allows us to adjust the frequency of the oscillations, we'll see something interesting. It might seem that the more we increase the frequency, the larger the amplitude of the oscillation will become. In other words, the more violently the spring will go up and down. The peak of the wave right here would just keep getting higher and higher. But interestingly, that's not what happens. If we gradually increase the frequency, we'll notice something interesting. At some point, the spring will reach its maximum amplitude, the strongest oscillations up and down. But then if we continue increasing the frequency, the amplitude will decrease. So even if the spring is being shaken faster, the amplitude of the oscillations will actually be lower. Of course, this is not exactly a very scientific demonstration, because here I can also change the force I'm applying, not just frequency. There is a good video that demonstrates it very clearly, not by hand, but by using a mechanism. I'll leave a link to it in the description. So when the amplitude of the spring's oscillations was at its maximum, that meant that the frequency at which we were shaking it matched the spring's natural frequency. That's resonance. Another good intuitive example is pushing someone on a swing. Let's say they're already swinging at a certain frequency. I'll come over and start giving them a push. Anyone who's ever done this knows that to achieve the maximum amplitude, you have to push at specific points and at a specific frequency. If we push too frequently and our pushing doesn't match the swing's frequency, we'll just end up making a mess of things. We can also remember the idea that you can shatter a glass with your voice. Here too, simply yelling as loudly as you can isn't enough. It will shatter precisely when the frequency of the sound matches the glass's natural frequency. It will go into resonance, when the amplitude of the oscillations will increase dramatically and the glass may shatter. The phenomenon of resonance is widely used in music and in many other fields as well. For example, I once made an entire video about orbital resonances. The natural frequency of an object or a system depends on its shape, size, and structure. A tuning fork produces a specific sound determined by its fundamental natural frequency. If you make it larger, the sound will change. The same goes for the metal bars of the glockenspiel, which come in different sizes. Now let's get back to Earth. We've already established that the Earth's surface and the ionosphere form a waveguide for electromagnetic waves. The waveguide is not a simple one. I've already pointed out that unlike a tube, for example, it is closed. And closed waveguides can act as cavity resonators. In other words, the waves don't simply travel from one end of the waveguide to the other. Instead, they are repeatedly reflected off the inner walls, and most importantly, if we introduce waves into this resonator at a frequency that matches the resonator's natural frequency, or one of its natural frequencies, since there can be several, then waves traveling in opposite directions can form standing waves inside. Does the Earth have a natural frequency? The moment you hear the phrase Earth's natural frequency, it's pretty easy to see why esotericists and people who are into all kinds of vibrations start rubbing their hands together and seeing something mystical in it. Does this mean that Earth vibrates at some particular frequency? Is this the heartbeat of our planet? What if we synchronize ourselves with it? Well, if you present it that way, it can certainly sound mystical. But You can only reason like that if you have no idea what this frequency actually is. It is not the frequency of the entire Earth. It's the natural frequency of the resonant cavity formed by the waveguide between the Earth's surface and the ionosphere. There are actually several of these frequencies and there's no magic involved. Let's say an electromagnetic wave is emitted from some point on Earth. We'll discuss where these waves come from later. If it has the right frequency, resonance can occur. We've already established that waveguides of different sizes are suited to waves of different wavelengths. Short wavelength optical waveguides are small, while microwave and radio waveguides are larger. A closed waveguide with a resonant cavity the size of the Earth would have a very low natural frequency. And for resonance to occur as the wave travels around the Earth, the number of reflections must be an integer. If you've come across posts about the Schumann Resonance, like the ones I mentioned at the beginning, or seen anything about the frequency of the Earth, you've probably encountered the value 7.83 Hz. Where does it come from? First of all, electromagnetic waves travel at the speed of light. Second, the Earth's circumference is approximately 40,000 kilometers or about 25,000 miles. The wavelength, that is the distance between two successive peaks, can match the Earth's circumference and be approximately 40,000 kilometers. Roughly speaking, the distance around the Earth is equal to one wavelength. The distance of a few dozen kilometers to the ionosphere is negligible compared to the tens of thousands of kilometers, and the thickness of the ionosphere is greatly exaggerated in these visualizations for clarity. If we divide the speed of light at which the wave propagates, 300,000 kilometers per second, by 40,000 kilometers, which is the circumference of the Earth, we get 7.5. 7.5 oscillations per second, or 7.5 Hz. It's not exactly 7.83 Hz, but the thing is, in these simple calculations we used approximate figures and didn't account for all the nuances related to the ionosphere. But I think the logic is clear. So with these simple calculations, we've more or less predicted the fundamental frequency of 7.5 Hz. But experimentally, a slightly different value is measured, 7.83 Hz. Although in reality it also varies over time. The 7.83 Hz frequency is the fundamental and strongest Schumann resonance. But there are other harmonies as well, although more energy is lost at those frequencies, so they are weaker. They are 14.1 Hz, 20.8, 27.3 and 33.8 Hz. But so far we've overlooked one important point. What is actually the source of the electromagnetic waves that resonate inside the waveguide cavity between the Earth and the ionosphere? The main suspect here is lightning. Lightning is incredibly powerful, and it emits electromagnetic radiation. We can literally see some of it with our own eyes, because the radiation is in visible range, and in other words, it is light. But lightning discharges also produce other types of radiation that we can't see with our eyes, including radio waves, and also those with very long wavelengths or very low frequencies. ELF radiation stands for extremely low frequency radiation. Its wavelengths can be tens of thousands of kilometers or miles long, with frequencies ranging from 3 to 30 Hz. And as you may have noticed, our waveguide's resonant frequencies fall right within this frequency range. So lightning strikes in the atmosphere, emitting electromagnetic radiation across different frequency ranges and wavelengths. But because this happens inside a waveguide, the frequencies or wavelengths that match its natural resonant frequencies become, in a sense, trapped inside the waveguide. And they are reflected back and forth many times between the ionosphere and the Earth traveling around the planet. And now one more important point. Lightning strikes Earth frequently. At any given moment, there are on average around 2,000 thunderstorms happening across our planet, and every second there are between 50 and 100 lightning strikes. An individual wave gradually loses energy and fades, but our waveguide is constantly being pumped with new waves. They propagate in different directions, and eventually a resonance builds up and standing waves form. So, in theory, if all of this really happens, we should be able to detect a signal from these resonances at any given moment. By the way, they're called Schumann resonances because the main theory behind these resonances was developed by Winfried Otto Schumann. In the early 1950s, he published several scientific papers on the subject describing essentially everything we've talked about today. The idea of the waveguide formed by the Earth's surface and the ionosphere, the calculation of its resonant frequencies, the proposed mechanism for generating the waves through lightning, and so on. Actually, the idea that the Earth and the ionosphere could act as a waveguide had been proposed earlier, as far back as the beginning of the 20th century. And a number of authors had proposed similar or related ideas. There's even an entire paper that lists examples of this. The existence of the Schumann resonances was confirmed a few years later after his papers in 1960. Detecting these resonances is not easy. The signal is extremely weak and can easily be drowned out by much stronger sources of radiation, as well as all the radio noise generated by our technology. And yet, modern sensitive equipment and digital signal processing techniques that allow us to separate the useful signal from the noise make it possible to detect them. There are several stations around the world that monitor the Schumann resonances. Here are the observations from different stations. One of these stations is located in Tomsk, Russia, and many of the images accompanying the post I mentioned at the beginning are actually spectrograms from the Tomsk station. But there seems to be a lot going on here, so where exactly are the Schumann resonances? These graphs are generally called spectrograms. The official website of the Tomsk station defines them as follows. A spectrogram of ELF noise is a graphical time-frequency representation of the amplitude of electromagnetic oscillations in the extremely low frequency range. Here we actually have not 2, but 3 dimensions. The vertical axis shows frequency, while the horizontal axis shows time in hours. The third dimension is represented by color. On the right you can see the color scale, which indicates the intensity. Black represents the weakest signal, while white represents the strongest radiation. See those broad horizontal bands that essentially stay in the same place from day to day? That's the signal from the Schumann resonances. The most clearly visible band comes from the fundamental frequency. And below that you can see the higher harmonics of the resonances, which become progressively harder to see because they are weaker. The frequency of 7.83 Hz is actually not constant. It changes all the time within a certain range, which you can see in these individual graphs showing how the frequencies of the different resonant modes change. This happens because our terrestrial waveguide is not ideal, the ionosphere isn't a sharp boundary, and its properties are constantly changing. They differ between the day and night sides because the sun has a major influence on the ionosphere. It also changes during different phases of solar activity and during solar storms. Then there is the fact that Earth itself isn't perfectly symmetrical, nor is its magnetic field, which is dynamic in its own right and also responds to solar activity. Atmospheric processes can vary as well. Different types of lightning, including upward lightning, as well as things like elves, sprites, and other forms of upper atmospheric lightning. From all of this, we can conclude that when some people attach spatial mystical significance to the frequency of 7.83 Hz, well, that's nonsense. It would be one thing if this were actually some kind of constant, unchanging pulse of the Earth. But in reality, the frequency of the fundamental resonance is constantly changing. Even here we can see that on a particular day it fluctuated from just 7.2 to almost 8 Hz. This image is constantly updated on the website, and I've seen spikes as high as 8.23. Not exactly magical. But the most interesting thing is that when esotericists talk about the Schumann resonances, they are not looking at these bands at all. And honestly, I get the impression that they don't really understand where the actual resonances they write so passionately about are on these images. They're looking at these black bands, calling them blackouts, and also they look at these white areas, calling them whiteouts, white fields, white infusions, and so on. And this is probably the funniest part of this whole story. They attach special significance to these areas on the graph. They write about these black bands, which they call blackouts, and I quote, "a point of absolute silence before a quantum leap." At this hour, you may have felt sudden disorientation or conversely a strange emptiness inside. Didn't feel anything. Think back. Interestingly, by that logic, virtually everyone on the planet should have experienced similar sensations almost 3 times a day, no less. And they also say that the blackout was a spatial anomaly and evidence of divine intervention. As for the white areas, they write, another quote, "We've entered a zone of continuous white light. This is the moment when the old firmware isn't just being updated, it's being wiped out." They claim that these infusions will help you reach a new personal individual level. Anyway, I could keep quoting this stuff for a long time. There's plenty more about quantum leaps, energetic transitions to 5D, and all the sort of thing. Some people even offer a service of a personal Schumann Resonance reading. And now for the funniest part. Do you know what these black bands and white spikes on the graphs actually are? Luckily, the official website of the Tomsk station explains everything for us. It's in Russian, but I'll translate. And I quote, "The black vertical bands indicate missing data. For some reason, no data was recorded." So basically, the station simply wasn't receiving data at that moment. It could have been due to a malfunction, a voltage fluctuation, the server going down, equipment being switched off for maintenance, and so on. What about the white spikes? The supposed energetic infusions? Well, the official website explains them too. These powerful spikes are associated with atmospheric phenomena occurring closer to the station, thunderstorms and lightning discharges, as well as more distant storms. The same official website also states that these spectrograms contain quite a lot of man-made signals. Quote, "The background is caused by the operation and emission from nearby power lines, transformer substations, and various machines capable of emitting electromagnetic waves in the ELF range. For example, the narrower, thinner lines are actually part of this man-made background noise." There you have it. A quantum leap. What's stopping these people from simply reading the description of what they're looking at? Literally on the same website they're getting these images from. And by the way, that's not even all the pseudoscience that gets attached to Schumann resonances. For example, you can find bracelets like these online, bracelets tuned to frequencies 7.3 Hz that supposedly help tune your body to Earth's frequency, allegedly reducing stress and pain, lowering inflammation, improving sleep, and protecting against electromagnetic radiation? What? It costs $50, by the way. First of all, what exactly is vibrating in it? And second, even if something is vibrating, so what? These are very weak radio waves in the atmosphere. And the bracelet does what exactly? In short, it's pretty obvious that this is nonsense. And what do you make of this claim? Apparently, the Schumann resonance is speeding up, supposedly causing time itself to speed up, to the point where a 24-hour day now feels like 16 hours. I don't even know how to comment on this. What does it even mean for resonance to speed up? Among the huge number of posts I came across while writing this script, I found posts that claimed that Schumann resonance jumped to 100 Hz, and so it provides direct access to a higher level of consciousness. What 100 Hz? Did the fundamental frequency of 7.83 Hz suddenly increase to 100 Hz? In that case, the waveguide would have to change dramatically so the Earth's size increased? Or are they talking about a higher resonant frequency? Which frequency increased? The fundamental frequency still hovers around 8 Hz even now, but at the same time, we've long known about frequencies above that. Apparently, those who write about 80 or 100 Hz don't even realize that there are several Schumann resonant frequencies. They just slap the number 100 on the spectrogram, not even seeing that the graph doesn't even go that high, and they just put it in a random place, say at 8 Hz. Basically, they're just making stuff up. And the most important thing is that there are actually people who read all of this and believe it. In short, this is a textbook example of how charlatans take a real physical phenomena and make up some nonsense around it to make what they do seem more legitimate and scientific. But interestingly, there is another side to this whole story. On various dubious alternative medicine websites, you can find claims that the effects of Schumann resonances on humans, on our health and our mental state, have been scientifically proven. Of course, they never provide any sources, but if you do the searching yourself, you can actually find a small number of studies. There are even studies published in scientific journals suggesting some correlation between the dynamics of the Schumann resonances and people's health. So what's the problem here? First of all, there aren't many studies like this, and they often involve very small sample size, sometimes just a few dozen people. But also, as we know perfectly well, correlation does not imply causation. I've already given plenty of examples of false correlations. Like the famous graph showing a strong correlation between the number of movies Nicolas Cage appeared in and the number of people who drowned in swimming pools. Nobody would think that one causes the other. Or I really like this image. To determine whether we are dealing with a false correlation or a real one, we'd need to couple of things. It would be good to run a control experiment, conduct similar studies in conditions where Schumann resonances don't affect people, and compare the results. But for that, we'd need to, for example, leave Earth. Preferably, we'd send a lot more than just a few people into space, because the more people we have, the larger our control group would be. And they need to stay there for sufficiently long time. But there's another problem. People would be in completely different conditions, exposed to microgravity, cosmic radiation, isolation, and many other factors. And it would be difficult to determine whether differences in how they feel in their health were caused by the absence of Schumann resonances or by the new conditions of space. You could put a person inside a Faraday cage on Earth, but that wouldn't be exactly the same as normal life on Earth either. You'd also need a lot of people for a proper study. In general, there haven't been any large significant control studies of this kind so far. That's the first point. And of course, none of the studies that do exist talk about any quantum leaps or transitions to new energetic levels. The possible effects they discuss are much more mundane. Things like effects on melatonin production or blood pressure. Next, let's say we have a hypothesis. Schumann resonances affect people's physical and mental state. For that hypothesis to be taken seriously, we also need a plausible mechanism by which this effect could occur. And this is where things get shaky as well. Sometimes people start claiming that the frequencies of the Schumann resonances match the frequencies of human brain waves, particularly alpha and theta waves. The idea is that the Earth's natural rhythm matches the rhythm of the human brain and can therefore have some kind of calming effects or something along those lines. Well, first of all, we've already established that this frequency isn't constant, it changes. And the same is true for both Schumann resonances and brain rhythms. They don't match up one-to-one. Even if they did match, how exactly one would affect the other? The Schumann resonances are incredibly weak electromagnetic waves with extremely long wavelengths. They are orders of magnitude weaker than any other radio signal that already surrounds us constantly, and weaker than the Earth's magnetic field. And we know that the effects of electromagnetic waves become stronger as the frequency increases or as the wavelength gets shorter. We feel heat from sunlight, X-rays and gamma radiation can harm us. But what about radio waves, especially ones this weak? Do we have an antenna in our heads capable of receiving a Schumann resonance radio signal? In simple terms, the longer the wavelength, the larger the antenna needs to be to receive the signal. For example, a dipole antenna should be half a wavelength long, while a monopole antenna should be a quarter of a wavelength long. Now let's remember that the wavelength of the fundamental Schumann resonance is 38 to 40,000 kilometers. An antenna, 10,000 kilometers or 6,200 miles long? Do you have one of those in your head? Well, okay, I already mentioned that there are several stations that detect Schumann resonances. Clearly, they don't have antennas that huge. The thing is, you can use loading coils connected to shorter antennas, which effectively increases the antenna's electrical length and allow it to receive shorter wavelengths. Again, real-world stations are more complicated, and they also need ways to separate the signal from the noise. But as far as we know, we don't have any comparable mechanisms in our heads that would be capable of receiving radio waves like these. So, even if some correlations are found, the mechanism is still a problem. That's why in most cases scientists remain skeptical about the effects of Schumann resonances on humans. This reminded me of the story with geomagnetic storms. There have also been a number of studies showing positive correlations, but it's still unclear how such weak fluctuations in the magnetic field could actually affect people. We haven't discovered a mechanism for magnetoreception in humans yet. I actually made a whole separate video about that. So at this point we can't rule out the hypothesis that Schumann resonances are somehow connected to people's physical or mental state with 100% certainty. But the evidence is not particularly strong, and it's not clear how such an effect would actually work. In any case, even what the existing studies on this subject suggest has absolutely nothing in common with all the stuff esotericists say about quantum leaps. But if you search for papers on Schumann resonances in scientific databases, the vast majority of them will be about something completely different. About studying the phenomenon itself as well as how it can be put to use. For example, since the resonances are caused by lightning, monitoring the resonances can be used to track thunderstorms and lightning activity on Earth. Furthermore, the number of thunderstorms and lightning strikes is linked to the climate, and if global temperatures rise, there will be more lightning, which can also be tracked through the Schumann resonances. They can also be used to detect lightning in the upper atmosphere, including the sprites and elves I mentioned earlier, and even processes occurring on other planets and moons. There are several bodies in the solar system that are candidates for having similar Schumann resonances, bodies with solid surfaces and atmospheres of varying densities. Mars with its thin atmosphere, and Venus and Titan, Saturn's moon, with their dense atmospheres. We can try to detect resonance signals at the frequencies expected for bodies of these sizes, which could indicate the presence of lightning on these worlds. Saturn and Jupiter have also been proposed as candidates, although the configuration would be different due to the lack of a solid surface. Resonant cavities could still exist in their atmospheres, and evidence of lightning on Jupiter has already been detected. So what conclusions can we draw from all of this? First of all, are the Schumann resonances the pulse of the planet? No. They aren't actually related to the entire planet itself that much. All the signals are generated in a thin layer of the atmosphere. It's certainly a part of the planet, but the entire planet is not vibrating at these frequencies, as some people claim. Next, what the esotericists on social media are saying is guaranteed 100% nonsense that has nothing to do with the reality and science. Either they simply can't read, or they deliberately ignore their real explanation so they can sell you a personal Schumann resonance reading, or some other service dressed up in the appearance of science. There is a small number of studies showing some correlations between people's state and Schumann resonance, but they involve small sample sizes and there are problems with establishing a proper comparison group. And most importantly, there is no clear mechanism for how such an effect could work. But it's possible that we'll learn something new about this in the future, so we can't completely rule it out. But the actual science of Schumann resonances is genuinely fascinating, and if it can also help us learn more about other planets, that would be even cooler. Thanks for watching. Links to all of the sources are, as always, down below in the description. And if you enjoyed the video, leave a like, comment, and subscribe for more videos in future. Bye.